So remember we talked about that quantity pass. Did we talk about the quantity pass-through when we talked about pass-through? It was how much, when there's an increase in the quantity that someone else is producing, you allow the total industry quantity to increase, right? Well, that's exactly what determines which is equal to the regular pass-through rate. That's exactly what determines this, right? Because if when the other guy's quantity increases, you let the whole industry quantity increase, that means that, if the whole industry quantity increases more than 1 for 1 in that case, then you'll have to increase your production to make up the difference. If the whole industry quantity increases less than 1 for 1, you'll have to reduce your quantity in order to do that. And so if the pass-through rate is less than 1, you have strategic substitutes. If the pass-through rate is greater than 1, you have strategic complements. Now, our simple example had constant elasticity demand, right? And therefore, you had a pass-through rate greater than 1. OK. So let's solve this out in our case. So remember that we had that the quantity of the second firm is equal to the quantity of the first firm multiplied by the square root of 2 plus 1 over the quantity of the first firm minus 1. Another way of putting that is that the total quantity of the industry as a function of the quantity of the first firm is just going to be if we add to quantity 2, quantity 1. So the total quantity is going to be Q1 plus 1 over Q1. And note that that means that as I increase Q1, this is going to rise less than 1 for 1. It's going to rise more than 1 for 1, I think. Yeah, it's going to rise more than 1 for 1 because the other guy increases his quantity as well with my increase in quantity. OK, so what is my profit function then going to be, Kevin? If this is the quantity as a function of my quantity.
Then your price is going to be 1 over Q. So
Exactly.
multiplying that by the price would give you the total revenue.
Yeah.
So that would be that entire thing over big Q. And then you want to subtract off the costs, which is
Constant marginal cost, right?
Oh, right, okay. So
Of 1.
Of 1, okay,
Yeah.
so it's just that minus 1.
Yeah, well, it's that minus Q, right?
Yeah. Oh, right.
So it's Q1, my quantity, divided by my price, times my price, which is 1 over the quantity. So that's just 1 over this thing in the square root, minus this whole thing, right? So that's not too complicated, right? Sorry, minus my quantity, right? So that's not too complicated. So what is what is going to be my optimal quantity then, Jing? Can you solve for the optimal quantity?
So you take the derivative of the
Yeah.
So,
Yeah? Why don't you come take the derivative of this?
Is minus 1 over 2 times 1 plus 1 over Q1 to the negative 3 over 2 times negative 1 over Q1 squared minus 1.
Yeah, that was good. Well done. Yeah, so you get this, which is exactly what Jing just said. She did it in her head. So you solve this out, and you get 2 times Q1 to the 4/3 plus Q1 to the 1/3 is equal to 1. So you have to plug that into Mathematica to solve for it, but Mathematica gives that the optimal quantity is 0.1, which is way below the 0.5 that we got from this graph, right? So that means that the first firm reduces dramatically its quantity, right? And the other firm is also going to reduce its quantity, right? So the other firm, if this firm's quantity is 0.1, this other firm's going to have a quantity of like almost nothing, right? And so the total industry production just like plummets when we move to Stackelberg. Because basically, by reducing my production, I get the other guy to so dramatically reduce his production that we almost get to, actually we get, I think, do we get past collusion? perfect collusion. We probably don't get past perfect collusion, but we probably get pretty close to perfect collusion. Okay. So a few things to notice. The first is that even with many firms, I actually think you might get past perfect collusion. That's kind of interesting. Anyway, even with many firms, prices can still be above costs. And on Thursday, we'll talk about the extent to which they fall as prices, as the amount of competition increases. But prices will typically be between monopoly and perfect competition. Now, I think actually in that Stackelberg example, they might actually be even higher than they are under monopoly for these strategic reasons we were talking about. But typically, they'll be between monopoly and perfect competition. So one of the most interesting results, some of the most interesting results come from the case where the firms are not symmetric to one another, as we've been assuming so far. So imagine that each firm has a different cost. So again, they price according to this equation. Notice that the markups of firms are always proportional to their quantities multiplied by the derivative of price. But the derivative of price is the same for everyone because everyone faces the same common demand curve, right? So the lower cost firm is going to have a higher markup, right? But the high cost firm is still going to produce some of the good, right? They won't produce zero. They'll just produce less, right? And that's inefficient, right? That's a waste. Neither monopoly nor perfect competition would do that, right? Because a monopolist would always produce efficiently, right? And in perfect competition, we know from the welfare theorems that everything's efficient. So when there's oligopoly and firms are different, there can be what's called productive inefficiency, where even conditional on how much is being produced, it's being produced in an inefficient way, right? Okay. So if we then add up across firms, we get that the sum, that the total quantity times derivative of price times n times the price is equal to the sum of the costs, or that the average quantity that the firms produce multiplied by the derivative of price times price is equal to the average cost, right? And so what that says is that if any one firm's cost increases by $1, that has exactly 1 over n of the effect that would occur if all firms' costs increase on price, right? And so what that means is that only the average cost matters, right, in determining the effect. And that means that heterogeneity among firms, while it affects this productive inefficiency, is not crucial to the overall level of prices in the market. Only on average what firms' costs are matters, not exactly the nature of the distribution across firms, right? And that makes the model somewhat robust to the introduction of heterogeneous costs. If different firms have a little bit different costs, the qualitative features of the model don't change very much. In fact, if you introduce some like dispersion in the firm's costs, it won't change anything at all as long as the average cost stays the same in terms of the aggregate price. But there will still be an inefficiency, which is that not enough production gets reallocated to the most efficient firms. Okay. So what we've been studying so far is called a game. So these are strategic situations where there's a small number of firms that make choices here of prices or quantities or of qualities we might talk about. But more broadly, games can be used to study many things. So who do you date? Where do you eat? People can make choices about all sorts of stuff. The key is that people's payoffs depend on what other people are doing. My profit depends on your quantity and so forth, right? And people take their actions simultaneously as in the Cournot game. And that's called a normal form game, when everyone takes their actions at the same time. Or they could take action sequentially. One firm takes an action, then another firm takes an action. That's called an extensive form game, right? Now, like in competitive equilibrium, we need some way to think about what's the solution to a game. In competitive equilibrium, we said everyone maximized their utility, taking as given the prices in the market. Here, it depends on exactly what you assume people take given about other people's behavior, because they're no longer taking as given the prices, right? And the most famous concepts build on the work of John Nash, and in particular, the two most famous solution concepts are going to correspond exactly to the way that we solved these situations before, right? So the first is called Nash Equilibrium, and this corresponds to how we solved the Cournot model. It says that every firm takes as given the strategy of all the other firms. And in that sense, strategies are not what firms choose, but rather what firms take as given that other firms will do, right? And each is going to optimize its decisions taking as given whatever the strategies of the other firms are. And then you find the equilibrium from the intersection of these reaction curves. Now, with two firms, that's just in 2 dimensions. In multiple dimensions, it's a whole system of equations. But it's the same basic idea, just as you found market equilibrium by the intersection of two curves in the case of there being only one good. And then in multiple dimensions, you had some multidimensional thing. Here, too, when you have two players, you can find the intersection by just two curves. And in many dimensions, you're going to have some big system of equations. OK. The second notion is what's called subgame perfect equilibrium, which corresponds to the Stackelberg model. This is one where one player acts first, taking as given how he knows that the second player will react in the second stage to what he did in the first stage, right? And there could be a whole sequence of actions. So for example, chess is a normal form game. I take an action given what I anticipate you will react to that action, which is based on what you anticipate I would react to that action, which is based on et cetera, right? And so the way that you solve these things is by backwards induction. You look at the end of the game, you say, what would someone do in reaction to what happened there? What would the person before him do in reaction to that? And in chess, the way that Deep Blue works is exactly by that. It looks way down at many situations that could arise, looks at how good or bad those situations are, and then tries to figure out how people will act backwards from there, right? Okay. Now, we're not going to use game theory very much in this class, but it does apply to a broad range of situations with a small number of people in these sort of strategic relationships with one another. Okay. So under this broad concept, the key question is, what strategies do firms actually use, right? We assumed that the strategies that firms used were quantities. That is, that firms took as given the quantities that other firms produced when they chose their quantity. They assumed that the other firm's quantities would be fixed when they chose theirs. But the question is, do we really think that it's the case that when firms choose their quantities, they take as given the quantity produced by other firms? You know, why not take as given the price that other firms are charging? Why not assume that that won't change when you change your quantity? Ryan, what would happen if we did that? What if firms took as given the prices that other firms charged?
Well, if they take as given the prices that are charged, then they could simply price their product slightly below that price, and they would get everything since they will have the lowest price.
That's right. Yeah, so that is exactly the argument of Bertrand and of Edgeworth. So they imagined a case where there were several identical firms with constant marginal cost, each taking as given the prices of their rivals. And Terrence hasn't showed up.